Welcome to Beyond the Lab. Have you ever wondered why objects fall to the ground? You may think it's a simple concept, gravity, but is it really? Let's find out. All right, let's get started. So as you know, if we have a stick figure right here and we have a planet, let's just say Earth, this stick figure would be dragged downwards. And why is that? Well, all large bodies have an amount of gravity. But don't be mistaken by this illustration. This isn't actually how gravity works. In reality, around a celestial object like a planet or a star, the space-time around it will be distorted. This is called space-time distortion. This is a theory that Einstein had in the 1900s, the early 1900s, that instead of a planet dragging in force and objects as a normal force in the four fundamental forces, the strong and weak nuclear force, the electromagnetic force, and the gravity, instead of having forces being dragged downwards like this, it's actually it's a distortion of the space surrounding it. So an object, as you would imagine, would rotate around it. So how do we know that it's a distortion of space-time? Well, of course, you can't know everything for sure. We've learnt that through times and times of theories in the past. So in 1919, there was a famous solar eclipse, probably the most famous solar eclipse in science history, where there were the stars in the sky. If the gravity was a distortion of space-time, it would be warped by the sun's gravity, and with that, the stars should appear out of location, not where they're supposed to be. So we can find this with our predictions of where the stars are. So how does this show that gravity is a distortion of space-time? So if gravity was a force, it wouldn't attract the stars, the light from the stars. But if gravity was a distortion of space-time, the light have no choice but to bend around the space, because the light is traveling through that fabric of space, and since it is bent and warped, so will the path of the light. So where did gravity all begin? So you would probably already know Newton. He was a extremely brilliant physicist in the 1600s to the 1700s, and although the apple dropping on his head is slightly exaggerating it, but he did look at apples dropping from trees and wondered, why does that happen? So if we have a tree here and an apple drops from it, now we would know that it's because celestial bodies attract. So a visual description of how this works with the apple may be difficult, because we're in the third dimension, and these visuals must be represented in fourth dimension. So here's an example of why we can't present them. So if in so the rotational solar systems we view as this, a orbit of a planet around a sun or a star. So that's how we view the orbit. But in reality, this is what it looks like in fourth dimensions, shown in second dimensions. Shown in 2 dimensions, I mean, sorry. This is the fourth dimension visuals represented in 2 dimensions. So this is actually how it rotates around the sun. So why is it stay in position? Why is it not just collapse inwards to the sun? Well, we know why it's not fly outwards. That's because of the gravity from the sun. But why is it stay inwards? Why does it not go inwards? Well, that's because of inertia, or in simple terms, the planet's forward motion. That's because when the planet is rotating, it's moving this way. So you could say it's centripetal force. So it's like inertia, the forward motion of it. It's because of inertia, forward motion, and you could say centripetal force, which is similar to centrifugal force, but instead of something in centrifugal force, it stays out. The centripetal force is the force acting on it inwards. All right. Now, if we want to get into technical terms, and you want to learn, say, the formula of gravity, I'm going to explain it simply. This is the formula of gravity. So this is how to calculate the gravity of an object, mostly used to calculate the gravity of a celestial object. So this F means the gravitational force. So the F means the gravitational force. All right, what about the G? G means gravitational constant. So that's the gravitational constant. And these two M's, it's mass 1 and mass 2. So the two masses you want to measure, so the gravitational force between those two objects. So say we have object 1 and then object 2. So then that would be the two masses we have. So this would be, instead of object 1, we would say this is mass 1 and this is mass 2. So now we get into this part, the R. R means the distance. So here it says R squared. So then we do the R squared. So the force would be the gravitational constant multiplied by this, which is mass 1 times mass 2 divided by distance squared. So I hopefully that simply explains this formula. All right, some of you might say that there is still much more to explain. Einstein's relativity and special relativity. but that's much more complicated if you get into it. So this concludes our video today. I hope you enjoyed Beyond the Lab. This is Declan. See you next time.